Hello everyone, welcome to Field for Science YouTube channel and I am Chetan Fulaure. In previous video, we learned about water supply system and in this video, we are going to design that water supply system. So let's get started. So in last video, we learned about 4 components of water supply system which are shown here. The first one is source, second one is pumping machinery, third one is storage tank and the fourth one distribution network. Later on, I told other fifth component which was rising main. We will learn about designing of these components one by one and in next video we will cover rising main and distribution network. But before that we need to find out one parameter which is most important parameter in designing of water supply system and it is demand. So what is demand and how to find that demand? Let's take previous village example. In that, there were some houses. Villagers needed water and that village population of this year we don't have. To find out that, we will need previous year's census population. We can get previous year's population from census website. Let's say for the year 1991, 2001 and 2011, population of village were 1000, 2000 and 2500 respectively. Now, as every person need water for activities like drinking, washing and cooking. We will assume here each person needs 55 liters of water in a day and technically it is called as 55 liters per capita per day or 55 LPCD. You might be thinking that why I have taken this random and odd number. The number I have taken is in reference to the new program of Indian government, that is Jal Jeevan Mission, which aims that every household should get tap connection and each person should get 55 LPCD. So we will calculate how much water this village will need in a day. For that, we will multiply our population of year 2020 with 55 LPCD. So this is our demand. But this demand we have got is for year 2020. But the scheme we are designing is for let's say 15 years. And after 15 years, our population won't be same as of today. So, if we design scheme for today's demand, then we cannot get sufficient water after 15 years. So, we need demand of year 2035. That is 15 years from now. So, how to calculate 2035 demand? If we keep our demand per person same, then we need 2035 years population. And it is found out by population forecasting methods. So, how to do this population forecasting? There are many forecasting methods which you can see on this screen. And you can choose according to their use which you can find in books. And I have also attached a link from which you can decide. But we are going to choose 3 methods which are arithmetic mean method, geometric mean method and incremental increase method. Each method has own significance and formulas of these methods can be seen here. By giving inputs like previous year census population, we will get forecasted population by each method. After that, we will take average of these populations. That's how we will get our final forecasted population. After solving, we will get village population equal to 4,392. So, we will get our demand also 2,41,560 liters. By finding demand, we reach one milestone in our design. Now, we will find out volume of ESR. This ESR should fulfill demand of village for a day. If we change frequency of water filling in ESR, then ESR capacity can be designed for half or 1/3 of demand. So, it will reduce volume of ESR needed and ESR cost will also reduce. If the demand is 2,41,560 liters and we assume filling of ESR 2 times in a day, then ESR volume will be 1,20,780 liters. As we found the ESR capacity, then what capacity of pump will be needed in terms of power? The power of pump is defined in terms of horsepower or HP. So HP of pump is calculated by simple formula and it is density of fluid into acceleration due to gravity into flow of fluid into total head of pump divided by efficiency of pump. We will see how to find each term here. As we know, here density of fluid means density of water, which is 1000 kg per meter cube, and acceleration due to gravity is 9.81 meter per second square. For flow rate, as we know, it is equal to volume upon time. As volume is demand here and our demand is 2,41,560 liters. Time normally means number of hours of water supply in a tank by pump. Normally, if it is solar pump, we will assume 8 hours of supply. To get demand in liters per second, we will take time in seconds. So after calculation, our flow rate will be 8.4 liters per second. In this flow rate calculation, if we accommodate 5% losses, then flow rate will be 8.8 liters per second. Now we will discuss about how to calculate total head. Total head is equal to static head plus velocity head plus friction head. Static head is elevation between suction pipe entry to delivery pipe end. Let's assume it is 20 meter here. Velocity head is v square upon 2g. Velocity v is given by flow rate upon area, and area is pi d square upon 4. Let's assume maximum velocity head as 2 meter, and friction head formula can be seen here. C is Hazen-Williams constant. It is 140 for HDP pipe and 100 for GI pipe. L and D are rising main length and inner diameter. Let's say in the village rising main length is 500 meter. Inner diameter is obtained from rising main design. Let's assume it is 75 mm as we will design rising main in later video. So after considering 10% losses due to bends, walls, we will get friction head of 29.34 meter. So total head will be 51 meter. Efficiency of pump can be taken from pump curve available at a seller. Here we will consider it is 70%. So HP of pump will be 8.6 HP. So we will use a pump which is available in market with HP close to 8.6 on higher side. Till now we have found out demand which is 2,41,560 liters, and from that we found out ESR capacity which is 1,20,780 liters, and we found out pump capacity which is 8.6 HP, and the designing of rising main and distribution network we will see in part 2. So thank you guys for design of rising main means selecting the optimized available standard diameter of the rising main pipe. If we survey some pipe in the market, we will get fixed diameter pipes, or in DSR document of each district where you can get all available diameters. To select diameter, we will use cost criteria as it is obvious. Means we will select diameter which has lowest total capitalized cost. There are 3 factors on which total cost of rising main depends on, which are pump cost, pipe cost, maintenance and energy cost. Now we will see this one by one. The pump cost is calculated by multiplying the cost of pump unit per kilowatt with total kilowatt energy required. This cost of pump per kilowatt required can be searched in the catalog of pump suppliers or from market. And kilowatt energy is nothing but power of pump we calculated in previous video. I would suggest watching first video for understanding this. Keeping all parameters same, the head calculated here is slightly different, which can be given as sum of the static head plus friction head loss plus other losses. Here we have replaced the velocity head with other losses, and the other losses are considered to be 10% of frictional head loss. And another thing is that in previous video we calculated power in HP unit, and for rising main we need that power in kilowatt unit. So we will multiply with 0.746. Now coming back to our equation. If we are using standby pump, then our kilowatt required will be this. Now another cost is total pipe cost. The total pipe cost is equal to the rising main length which we needed in meters into the cost of pipe per meter. We will get the rising main length from site survey. Pipe cost per meter will be different for each pipe diameter, which can be found out from story. The last cost is maintenance and energy charges, and these charges are a product of annual M&E charges and scheme design period. In our case, it was 15 years, that is from 2020 to 2035. The annual M&E charges are given by pump capacity in kilowatt into annual charges. Pump capacity we have already calculated. These annual charges are calculated by average pumping hours into energy charges per kilowatt hour into 365.25 days divided by 1000. These average pumping hours can simply find out by pumping hours at 2035 multiplied by average discharge upon discharge at 2035. Here, this average discharge is just average taken of demands of 2020 and 2035. Now, by addition of these three costs, we will get total capitalized cost for the particular diameter of rising main. Likewise, we will calculate this capitalized cost for other diameters. So, comparing different diameter pipes, you can get a diameter pipe which has minimum capitalized cost. This way, we have designed the rising main. Up to this, you can see this calculation can be very hectic. But don't worry. Soon, I will be coming up with an application which is built by me, and in that, you will get a desired output by giving input of required parameters. So, stay connected. Now, we will move forward to distribution network. For this, we need to find the optimized network in the sense of diameter, length, losses, and cost. There are softwares available such as Branch, but I will recommend you more optimized open source application, and it is Jaltantra, which is designed in IIT Bombay. I will show the website and the link is in the description. Here is the website. The application is available as a web-based application and desktop application. And here tutorial is also available, from which you can easily learn it. I will show just layout to you. So this is how web-based application look. Here in this section, you have to fill required data. And after giving inputs, just click optimize from this to get desired pipe diameters with cost, losses and pressure. You can save input and output in Excel, XML format from here. You can upload branch file also. So just go through the tutorial and you will understand everything. Thus, we have completed our designing of water supply system. Soon, I will show my application built for designing of water supply system. Till that, keep learning